Okay, so first thing is, I'm going to skip a tiny weird bit because I told you to take a look at this. Ooh, I don't know what that is. Okay, so first I want you to match the correlations with the plots below. Each correlation can only be used once. That will help you make better decisions. When I look at the first two, what do you know about them? Positive. When I look at the bottom two, can you tell they're negative? This one is kind of hard to tell that it's negative, but it is definitely negative. It makes a narrower band if I call it negative than if I tried to say it was positive. See how wide that band would have to be? So it's definitely negative. But what do you know about it? It's weak, so it's this one. And that makes the other negative a little stronger, right? So it's this one. Now we're looking at the positives. And when we look at these positives, we have this one and we have this one. Oops, I kind of got wonky. This one. So, which one is stronger, the one on the right or the one on the left? The right. He is stronger, therefore he must be a 0.73, correct? All right, now let's go back up. Some of this was in your information today in your PowerPoint. Which one of the following have no unit of measure? Does a median have a unit of measure? Yes. Does S squared, standard deviation squared, does it have a unit of measure? Yes. Yes. He has a unit of measure. Does R have a unit of measure? No. Does the mean X bar have a unit of measure? Yes. Does the IQR have a unit of measure? Does standard deviation have a unit of measure? Does the standard deviation of the residuals have a unit of measure? Does your Z-score have a unit of measure? No. Its unit of measure is this many standard deviations, and I don't think a standard deviation is a unit of measure. Like, that would be weird. So he has no unit. What about mu? He has a unit. Okay, so those are the only two you should have circled. Which of the following are not resistant to outliers or a few extreme values? So let's talk a little bit. Is the mean resistant? Okay, so mean is not resistant. Right? Now, anything built off of the mean is also not resistant. Remember that. Your mean is not resistant. So, is the median, okay, which of the following are not resistant? The mean is not, which also means X bar would not be resistant. Now what? Standard deviation is not resistant. Is the Z-score resistant? Z equals X minus anything dealing with the mean is not resistant. So standard deviations are not resistant. What about the IQR? Is it resistant? It is resistant, so we won't include it. What about your R value? Is it resistant? No, it is not resistant. Remember, people that fit well help our R. People that are outside hurt our R. So R is not resistant. And what about the median? Is it resistant? Yes, it is resistant, so I won't include it. That's kind of hard how it's like, will you include it, will you not include it? It's a wording thing. All right, scrolling down. True or false? You must explain why and correct it. So first, r squared is 0.49. Then the correlation R value is 0.2401. No. How are the R and the R squared related? Yeah, R squared is the square of R. So in order to get R, I need to square root. And when I square root 0.49, I get 0.7. Does that equal this? So this is a false. Also, a big reminder, check the sign. If you have a negative scatter plot, R is negative. If you have a positive scatter plot, R is a positive value. Right? You got to check. You don't just square root. You square root and think about the sign. Least squared regression line of y on x makes the sum of the vertical distances of the data points from the line as small as possible. That is true. Our goal is to make the residuals as small as possible. In symbols, the least squared regression line minimizes the sum of y minus y hat. This is false. You're like, but you just said true. But it's false. Why is it false? What's false? The last part, because what's missing? It's called a least squares regression line. What was the equation missing? The square. So the equation was missing the square, therefore it gave you a right statement but a wrong equation. Guess where the equation is? So you can always check it. You can be like, this has squares and that's not squared and shouldn't be squared. And then you'll be like, oh, look. Boom, right? Hey, is whoever's on that phone more important than me right now? No, thank you. Always great doing business with you, Carson. All right, number 6, extrapolation is the use of a regression line for prediction outside the range of values of the explanatory variable used. Do you agree with that? So if I have data from here to here, blah, 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 and I can see this relationship, and I make a line, can I use it to make a prediction out here? Okay, I could make a prediction, but would I say my prediction is going to be reliable? Right, so such predictions are often not accurate. That is true. It is often not accurate to make a prediction that's far outside of our data. A correlation, R, near +1 or -1, indicates that there is a strong linear relationship. We can show that the explanatory variable causes the change in the response by obtaining an R near ±1. False. 2 reasons this is false. Tell me one thing. Number 1, not linear unless the residual plot shows no pattern. And number 2, there's a second problem. This is something that Stevie tells you all the time. Yes, you cannot say cause and effect unless you see a randomly assigned treatment. Okay, no cause and effect without seeing the experiment. Okay, hold on. Look at the next one. Hello? Yes, yes, I'm tutoring. Yes, ma'am. Okay. Yeah. Mm-hmm. Oh, of course. No, I know. Of course. Okay, bye-bye. Okay. All density curves are symmetric. Are all density curves symmetric? No. And within one standard deviation of the mean is 68% of the observations? No. All density curves are not symmetric. That is false. Within one standard deviation of mean, there's 68% of the observations. So this is false. If we said all normal density curves are symmetric and within one standard deviation of the mean, there's 68% of the observations, then I would say yes. That's only talking about a normal curve, but they're bringing it kind of into everything. A couple questions on this do go back to chapter 2, but not a lot. And then in our second review, none of them will go back. It's all chapter 3 in the next review. This is a short little review. Was that our last question there? Yes. Okay. Choose the correct answer and circle it. It's multiple choice. Suppose the correlation between two variables is r equals 0.12. What will be the new correlation if 0.25 is added to all the y variables, every value of the x is doubled, and the two variables are interchanged? 0.12. Why? That's right. R does not change when you change units. R is independent of units. It's independent of who you assign x and y. It doesn't matter. R will stay the same. Data are obtained from a group of AP Statistics students by examining the number of letters in their full names and the Scrabble values of their names. The resulting least squared regression line showed a correlation of 0.83. What percent of the variation makes you think what? R squared. What percent of the r squared in the Scrabble value can be explained by looking at the linear relationship with the number of letters in the name? Is the correlation equal to the r squared? No. Remember, the r is 0.83, so the r squared would be the square of 0.83, which would be 0.69 or 69%. So that's A. All right, next. Okay, so you're picking which one is true. Okay, so talk to me about things that you know are false. Does a lurking variable have an effect? A lurking variable, another way to think about it is confounding. Confounding variable, does it have an effect? Yeah, a confounding variable has an effect. That's why we say, well, we have to have a control so we know what the confounding variables is doing and we can negate that variable. The mean and standard deviation of a normal curve are 0 and S is 1. Something's wrong with that. S is not standard deviation. That would be S sub X is 1. The standard deviation is 1, but they gave you the wrong variable. They gave you the variable for the residuals, and they made you, because I looked at that one at first, and I was like, oh, it's that. But it's not, because that's the wrong variable. The correlation coefficient and the slope sometimes have opposite signs. False. Your slope and your R and slope have the same sign. So that's a no. There is a very strong correlation between height and gender. All of the men are tall, all of the women are short. All women are tall. Can you say no? This is actually the right answer, and this is one that goes back to chapter 2. Who can remind me how, if I give you a percent and I want to find the z-score, how do I do it? Inverse norm. If you do inverse norm and your area is 0.10 and your mu is 0 and your sigma is 1, you will get z equals negative 1.28. So that answer is E. In a statistics course, a linear regression equation was computed to predict the final exam score from the score on the first test. The equation was y hat equals 8 plus 0.9x, where y is the final and x is the score on the first exam. James scored a 90 on the first test. On the final exam, James scored an 86. What is the residual? So the equation is 8 plus 0.9x. Y hat equals 8 plus 0.9x. So I'm going to give you a minute to do that. Okay, so I plugged in 90 since he got a 90 on the first test. 0.9 times 90 plus 8 is an 89. He had a 90, so your actual minus your predicted, no, sorry, he had an 86. 86 is his actual, minus the predicted, which is an 89. That gives me a negative 3. So the residual is negative 3. How would you say it? Somebody give me an interpretation. The actual score on the test is, yes, the actual score on the test is 3 points less than the predicted score. Perfect. Good job. All right. If a store runs out of advertised material during a sale, customers become upset and the store loses not only the sale, but also goodwill. From past experience, a music store finds that a mean number of CDs sold in a sale is 845 and the variance is 225, and a histogram of the demand is approximately normal. The manager is willing to accept a 2.5 chance that a CD will be sold out. About how many CDs should the manager order for an upcoming sale? So, this is inverse norm. Did you know that? Yeah, because they're giving you the probability. So 0.025 is your area, inverse norm. Your mu is 845. And then they didn't give us the standard deviation. What did they give us instead? The variance. So what do you have to do to the variance to get the standard deviation? Square root. Square root of 225 is 15. So second, well, this doesn't help us today or on our test tomorrow. It will help us with the test that is Monday. So that's why I'm still doing them and not saying let's skip them. So I have 815.6. Oh, goodness, y'all, I went the wrong way. I should rewind this, make it look like I'm smarter than I am. If there's a 0.025 chance that they're going to sell out, what is the probability that you will get a CD? 90.975. So sorry, second vars, inverse norm, 0.975. I'll draw that out and show that to you in a second. My B. 874.4, which is 875. So that's C. So think about this. So you have this, you have the mean of 845. That's the mean number that are going to be sold. And if we buy this many, you have it. And if we buy this many, you have it. And all of these, you have it. But there's this chance that if I hit this value, there is a 2.5% chance that they're not going to have it. But remember, probability always works with the left side. So we want to know the probability that you get it, and that'll tell us the value we have to order. Then if you hit any more, if some more people than that come in, they're not going to get it. That's a 2.5% chance that'll happen. All right, back to chapter 3 stuff. So can we predict the, sorry, I'm going to have to do some erasing. Can we predict the number of calories in a fast food burger from the amount of fat? Pause for a second. You have to decide who is X and who is Y. Does it matter? Yes. Who is doing the predicting? The amount of fat is what you start with. It's trying to predict calories. So who is X? Fat is X. And calories is Y. And you need to put this in list 1, and you need to put this in list 2. And that's a little wonky because sometimes we look at a table and what's listed immediately we go after, and this you kind of have to be backwards with. Okay, so after you get it listed in after you get it entered in your list, you need to go Stat, Calc, go down to least squared regression line, which is number 8 in a lot of calculators. It's down there lower. And when you hit enter, make sure you have list 1 and list 2 in your X and Y, and then you should get this information. That's what should be on your screen. So your A value, which is your y-intercept, is 210. Your slope is 11.06. Your r-squared is 0.923. And your r is 0.96. So which answer is it? Is it A? Because they gave you your r value. Why isn't it B? But they told you it was r squared. It's not what? Does it say find the regression and the correlation? So you do not want the r squared, you want the r value. Go ahead to the next question. I'm going to hit pause for a second. Go on to number. Bye-bye. All these people leaving me makes me sad, but I have the rest of you, and that makes me happy. All right. The mean and daily demand for bread at a popular bakery is 2,500 loaves. Okay, hold on. So 2,500 loaves is the mean. The standard deviation of 225. Every morning they bake 3,000 loaves. What's the probability that they run out of bread? So they are always over here at 3,000. So this is how much bread they have. What is the probability that they hit here or more? So we actually want to know this. Because if you're in the pink, then there was enough bread. If you're in the blue, there was not enough bread. So are we going to inverse norm or just norm CDF? Norm CDF. Second vars, norm CDF. My lower is 3,000. My upper is 10,000. My mu is 2,500. And my standard deviation is 225. Paste. Now, I got 0.0131. I might need to make my lower 3,001, my upper 10,000, but I don't think it's really going to matter. Because if 3,000 loaves are purchased, we have enough bread, right? But if 3,001 are purchased, we don't have enough bread. So that answer is 0.01298. So no matter what, it's pretty much 0.0130 or 0.0131. So that answer is B. Okay, I love this next question. I think it is really neat because it is the part B. We are going to solve for pieces with what we're given, and that's kind of neat. Okay, so the first thing you're going to do when you get this question on your test tomorrow, because it's going to happen, it is a guarantee, you are going to look at the equations on your reference sheet. And on your reference sheet, the first thing you're going to go after is your slope. And your slope says that B1 is R times S sub Y over S sub X. So B1, and I'm on A right now. So B1 equals R, which is negative 0.2, S sub Y is 6, S sub X is 4. And I have negative 0.3. Okay, so we know that that is our slope. So y hat equals something plus negative 0.3x. Or you could not do the plus and just have a minus there. That would be okay too. So B1 is always slope. Now, the next thing is B naught. B naught is y bar minus B1 times x bar. So B naught is your y-intercept. My y bar is 20 minus my B1 is negative 0.3 times my x bar, which is 30. And that gives me B naught is 29. So this is 29. Okay, now part B is a different problem. They give us different blanks that are missing. They gave us the y-intercept and the B naught. This is B naught. This is B sub 1. But we are missing R and we are missing X bar. Which do you guys want us to go after first? It doesn't really matter. X bar. Okay, so this is the equation that has X bar in it. B naught equals Y bar minus B1 times X bar. B naught equals, what is Y bar? 40 minus B1, which is 15, times X bar, and X bar is, I don't know. Well, oh, what did we have? We did have B naught, right? And our B naught is negative 10. Okay, so you're just going to solve that. So we have negative 10 equals 40 minus 15 X bar. So I'm going to subtract 40. Negative 50 equals negative 15 X bar, and I'm going to divide by negative 15. X bar equals 50 divided by 15, 3 1/3. X bar is 3 1/3, or 3.3 repeating. Okay, now we need the R. And the equation that you have tells you that B1 is R times S sub Y divided by S sub X. So my B1 is 15. My R, I don't know, so I'm just going to call it R. And then my S sub Y divided by S sub X is 15 divided by 0.8. So 15 equals R times 18.75. So R equals 15 divided by 18.75, which is like a Christmas miracle. We got back R is 0.8. Very nice. Okay, like I said, I'm promising you that you will see that tomorrow. You will see a question that deals with this stuff. So make sure you're familiar with your reference sheet. You know where they are. You're ready to use them. Do I have any questions about that before I move on from those? You will get the pink reference sheets. I'll pass those out tomorrow. All right, here's tutoring review number 2. So this is only this chapter stuff. This won't have any normal curve on it. And it's really nice. I like this. I did it today, and I thought it was pretty good. Okay, a least squared regression line was fitted to the weights in pounds versus age in months of a group of many young children. The equation of the line is this. Now notice, because they used variables, they had to go back and they had to define their variables. That's what I'm talking about when you write an equation. If you don't use words, you have to define your variables. A 20-month-old child in this group has an actual weight of 25. Which of the following is the residual weight in pounds for this child? Okay, how do I get a residual? AP. A minus P. So the actual weight is 25. I have that. I don't have the predicted weight, but I'm going to get the predicted weight by plugging in 20 for the number of months. And that gives me 29.6. So my residual is negative 4.6, which is B. All right, interpret that for me. The actual weight of a 20-month-old child is 4.6 pounds less than the predicted weight. So the actual is 4.6 less than predicted. Okay, a wildlife biologist is interested in the relationship between the number of chirps per minute for crickets and the temperature. So these are the chirps. This is the temp. Which of the following best describes the meaning of the slope? So we need to talk about slope, and that's in your PowerPoint that I gave you today. So you're reading these. They're wordy. Okay, so which one do you think it is? Yes, ma'am. Of course. Which one do you think it is? B. Do we agree? Okay. For every increase in 1 degree temperature, the number of chirps is predicted to increase by the slope. Yes? All right, good work. 100 lab rats has available both plain water and a mixture of water and caffeine in their cages. After 24 hours, 2 measures were recorded for that rat: the amount of caffeine the rat consumed and the rat's blood pressure. Okay, so the caffeine is X and the blood pressure is Y. The correlation between caffeine and blood pressure is 0.428. Which of the following conclusions is justified on the basis of this study? Okay, so take a minute to read those, and only one of the following is justified. We are on Tutoring Review number 2 in your note packet, and it's question 3. Okay, so the correlation between X and Y in the population of rats is also 0.428. Can we take something that is all of the rats that are in the lab and do something to them and say that holds true for every rat? No, you can't do that. If the rats stopped drinking the caffeine water mixture, this would cause, think about old Stevie. No, correlation does not imply causation. You can't say that. About 18% of the variation, whenever you see the word variation, what has to pop into your head? R squared. Can be explained by a linear relationship between blood pressure and caffeine. Well, I don't know. That's a possibility. How can I find R squared? Square the R. 0.428 is your R. You're going to square it. So 0.428 squared is 0.18318. So what can you say? Yes, that one I like. That one looks good right now. I would check the others. Rats with lower blood pressure do not like the water caffeine mixture. That's not true. Well, we don't know. That could be true, but we don't know that. And since correlation is not very high, the relationship between the amount of caffeine consumed and blood pressure is not linear. Remember, R does not tell you whether something is linear. You can't just look at an R and guess linear. You have to look at the residual plot. Yes, that's all you can say. All right, Number 4, a high school physics teacher was conducting an experiment with his class on the length of time it will take a marble to roll down a sloped chute. The class ran repeated trials in order to determine the relationship between the length in centimeters and the sloped chute and the time in seconds for the marble to roll down the chute. A linear relationship was observed, and the correlation coefficient is 0.964. After discussing their results, the teacher instructed the students to convert all the lengths of measurement to meters, but leave the time in seconds. What effect will it have on the correlation? So remember, the correlation is the R. What effect does all of this changing have on the R? It has no effect. Your R will remain unchanged. Because changing from centimeters to meters does not affect the value of the correlation will remain 0.964. Yes. All right, number 5, a delivery service places packages into large containers before flying them across the country. I'm going to give you a second on this one because I really like it, and I think I like it because I had to think really hard about it. Now, my friend Alex Jones will not have to think hard about this, but Sheffield had to think hard about this. That's probably why my sites were on the University of Florida and his sites are on things like, I don't know, University of Chicago and stuff. Say it again. I know. I'm just saying. Okay, so what do you think? Haley, what do you think? Haley says they're going to have a negative correlation. Do you agree? You're like, well, I don't know. I didn't know either. And the only reason I called on Haley is because I looked down at what she was doing, and it's exactly what I did. Haley drew a little graph. And Haley was like, well, listen, let's say that the maximum weight is 1,000 pounds. And you have package A and you have package B. If package A weighs 100 pounds, what is package B allowed to weigh? 900. But what if package A weighs 900? What is package B allowed to weigh? And if package A is 500, what is package B going to weigh? Or allowed to weigh? 500. Therefore, there is a negative relationship between the two. It took me a minute. I sat there and I looked at it, and like I said, I was only a University of Florida grad. I'm not like Alex Jones, who goes to these fine establishments and is competitive with all these people. I was just this kid who went to Florida. So I had to sit there for a second. I had to think about it. And then I drew it out. And because when I see it, it helps me. So then I started drawing it and thinking about this and how they had to have the same sum. And then when I plotted the points, I was like, boom, that's it. But I didn't get it right away. I didn't just look right at it and go, that's it. I had to think about it. All right. The computer output. So in today's PowerPoint, we talked about the computer output. What can we do with all of this stuff? Right now, we can get rid of it. In the spring, we'll learn how to use it, but right now, we don't know anything about it. So what we have now, what is this known as? Y-intercept, good. And this value is the slope. And this is the standard deviation of the residuals. And this is your R squared, which is your correlation coefficient. No, I'm sorry, coefficient of determination. Coefficient of determination. Your correlation would be the square root of 0.82, and you'd have to be able to look at the graph to pick a sign, or look at the equation. If the equation had a negative slope, you'd pick a negative. All right, so you have to answer this. Okay, so what do you know? It's the slope, so we know we're interpreting slope. So when I read these, this is the variability. That's interpreting R squared. Predicted concentration of lead is this when there's no concentrate. This is y-intercept stuff. So it's definitely A or B. And what the slope says is as the lead increases by 1 unit, the zinc will increase by 19. So as the lead increases by 1, the zinc is predicted to increase by 19. So is it B? It was kind of confusing. It was very wordy and kind of backwards. I had to think about it. Number 7, I heart number 7 because it's easy. Sometimes I heart a question when it's tough and it makes me think. Sometimes I appreciate those things that don't make me think. This one does not make me do a lot of thinking. Which one is absolutely perfect but negative? A. It's absolutely perfectly linear, but it is negative. And numero 8. In a recent survey, 60 randomly selected married couples from the same town were asked to rate the overall quality of living in their town on a scale from 1, which is poor, to 10, which is excellent, on 20 different attributes, blah, blah, blah. For each couple, the husband's individual ratings on the 20 attributes were averaged to produce an overall quality, and blah, blah, blah for the wife, and here they are. The R squared value is here, or sorry, the R value is there. Based on the scatter plot, I can't even speak. Based on the scatter plot, which of the following statements is true? So take a minute and look at these. Alex Jones, how much do you miss stats? He misses it a lot. You see, you miss me. Thank you, Alex Jones. We miss you too. I have been very grouchy with my stats kids the last couple of days because they dropped the ball. And Bless you. Okay, let's start from the bottom. For each couple, the overall rating assigned by the husband was the same as the wife. If that were true, every value would be perfectly square like this. Is that the case? No. So that's easy to mark that one off. That's why I went after that one first. The difference in overall ratings between husband and wife was not more than 3 for any couple. So I'm going to only look at the extremes here. And when I look at an extreme, it would be a person like this. So this pink dot, the husband gave it almost an 8. Let's say it's a 7.5. But the wife gave it a 3.5. The difference in their score is 4. Is that what this question is saying? Yeah, this question says the max would be 3, so that's not true. Throw it out. The range in the husband's ratings is greater than the wives'. Well, the extreme for the husbands are 9 to about 4.5. So 9 minus 4.5 is 4.5. That's the husbands. And if I look at the wives went from about 2.5 to 9, or 8.5, let's say. So the wives have a difference of 6. So that's not true. More overall rating of 7 or less was assigned by the husbands. No, that's not true. Because the husbands assigned, here is 7. The husbands gave 7 much more than the wives. The wives were the ones who gave, sorry, that was confusing. The wives gave many more 7s or less. So your answer was A. The husbands tend to rate the quality of lives better than the women. Because the husbands gave higher ratings and the women gave lower ratings. All right. Number 9. Oh, love number 9. The residual plots from 5 different least squares regression lines are shown below. Which of the plots provides the strongest evidence that its regression line is appropriate? So which one shows you that a linear model is appropriate? C. C is the best. It shows a random scatter. D has kind of a fan effect. E definitely has a fan effect. This one is like a flock of birds. This one is parabolic. So it is definitely C. A student measured the heights and arm spans routed to the nearest inch of each person in a random sample of 12 seniors at a high school. A scatter plot of arm span versus height for the 12 seniors is shown. Based on the scatter plot, describe the relationship between the arm span and height for the 12 seniors. So this is an FRQ. Now, when you describe, what do you have to do? Doffs. So I expect to see direction, outlier, form, strength. It must be in context. You can, I'm not going to say kill multiple birds with one stone, but I'm going to say that you can eliminate many of these in one sentence. Okay, so we don't want to talk about killing birds. I don't want to upset anybody because I don't do well with people who cry. So if you start to cry, I'll get real uncomfortable. Right, Maddie? Maddie does. All right, what direction is it? Positive. What form is it? Linear. What strength is it? Moderate. So I would say there is a moderately strong linear relationship. Oh, positive, sorry. Positive linear relationship between height and arm span. Okay, now, is there, yes, ma'am?
So what if we said there was a strong one?
I think you'd be okay. I don't think, to me, if I change the scale on this graph, and yeah, you know what I'm saying? If I change the scale, these points would scoop together and it would look like it's very, very strong. I think they're pretty good. I bet you if we actually plotted these values, this would be like a 0.75 or greater. Yeah. Okay, so then the only thing I need to talk about now is an outlier. I think you could get away with saying there's actually no outlier. If you wanted to pick a point who was a possible outlier, this guy is definitely influential, but I wouldn't quite call him an outlier, but I wouldn't be upset if you said he is a potential outlier, or if you said he is an influential point because he would have a larger residual in blah, blah, blah. Okay, I would be okay with that, but I wouldn't say he's super outlier. You agree? I would say there is a potential outlier. You know, I can look at the answer key to this. Hold on. Do we have the answer key? It doesn't say anything about an outlier. Yep.
There is no outlier, but there's an influential.
Sure, totally. But he would be an influential point because he would have a larger residual, or because he is farther away from the rest of the points, or, you know, you could talk about him. All right, so let X represent the height in inches and Y represent the arm span in inches. Two scatter plots of the same data are shown below. Graph 1 shows the data of the least squared regression line and graph of this. And graph 2 shows the data for the line y equals x. Okay, so this is the exact same data. The only thing they've done is they have put two different lines on your data. Now, which do you actually think looks better? Why do you think graph 1 looks better? Are the points closer on graph 1? Graph 2, it has 2 points that touch, but then what about the rest of the points? Okay, so actually, I'm going to tell you the truth. Graph 1 is a better fit, but I think it's very hard to tell, but this is a real FRQ. Okay, so graph 1 is actually a better fit, and I'm happy that your gut took you to that, because it took me a minute to really look at it and pick which is a better fit. But, okay, the rest of the question leads you through graph 2 in just a second for a really good reason. I like this question. So, you see how graph 2 is the line y equals x? So, it's like the perfect slope of 1. All right, so on this next part it says the criteria described in the table below can be used to classify people into one of the 3 body shape categories: square, tall, rectangle, or short rectangle. So if you are square, your arm span is equal to your height. If you are a tall rectangle, your arm span is less than your height. Okay, so a tall rectangle would be a person who is tall but has short arms. That's the idea, okay? And a short rectangle is somebody who is wider. If they put their arms out, they're wider than they are tall. Okay, For which graph, 1 or 2, is the line helpful in classifying a person's body shape as square, tall rectangle, or short rectangle? Explain. One of these graphs helps you do the classifying. Which graph is it? Graph 2. Graph 2 is helpful because it shows the direct relationship between height, or is it arm span and height, or height and arm span? Height and arm span. Graph 2, or graph 1, I'm sorry, graph 1 does not show that because it has a slope other than 1 and a y-intercept other than 0. Graph 1 does not show that because the slope does not equal 1 and the y-intercept is not 0. Yes, ma'am.
If you put the relationship between arm span and height, would you get it wrong?
No.
Okay.
Because it is the relationship between arm span and height, height and arm span. Remember, they told us early on that if you're getting to write your own equation and the wording doesn't tell you which you have to choose, you can assign whatever you want. If you just have data, you can assign whatever you want. Okay, so now look back at this. And I want to talk about this, and I want you to look at the people. These two people are square. The blue dots, oh, I didn't see that person. The dots are 3 square people. Okay, now I'm going to go in and I see these people. 1, 2, 3, 4, 5 people. Why are they above the line? What is longer on them? Look at it. Arm span, like this person, is a 6971 because this is their height and this is their arm span. So their arm span is bigger than their height. So what are they called when their arm span is more than their height? They're a short rectangle. There's 1, 2, 3, 4, 5 short rectangles. And then I have these dots, and these 4 people would then have to be tall rectangles. So there's 3, 5, so there's 3, 5, 4. So there are 3 square. There are 5 short, right? Yep, 5 short. And there are 4 tall. And I would double check myself because that adds up to 12 people. And I would look back and I would make sure that it was 12 people because I may have a personal experience with this problem where I missed the square person and I only accounted for 11 people. Remember, I only went to the University of Florida. All right, here we go. I'm just kidding, Alex. I'm messing with you. Using the best model for prediction, calculate the predicted arm span for a senior with a height of 61. So like we talked about, the weird thing for this question is you flip back to graph 1. And remember, for graph 1 was the better fit. Therefore, we are going to use that equation in graph 1. We are going to use the equation that said 11.74 plus 0.8247. 11.74 plus 0.8247 times the height is the predicted arm span. So 11.74 plus 0.8247 times 61 . And I got the answer of 62. Yep. So I have that the person, so I would say, I could just show this work and I could say 62.05 inches, or I could write a sentence and say the senior with height 61 has an arm span of 62 inches. Has a predicted, thank you, predicted arm span of 62. Are we good? All right, so I'm going to be done.